Good morning, good evening, good afternoon. Whenever you are watching this video, let me welcome you all to our channel Future Endeavors. Okay, so quickly let us move on to our discussion. We have been discussing about the magnetic effect of current. In the previous lectures, we have seen that how a current flowing through a conductor can produce magnetic field around it, that is, can behave as a magnet. We have discussed about magnetic field, what are magnetic field lines, and we have also seen that the current flowing through a loop, conducting loop, can also produce a magnetic field. Also, we have discussed solenoid, that is electromagnets, and we have done a comparison between electromagnets and permanent magnets. Okay, so today we are going to discuss the next topic, that when a current carrying conductor is placed in a magnetic field, it experiences certain force. Why? Now, let us quickly move on to this topic. Today we will be discussing about the force acting on a current carrying conductor placed in a magnetic field. Okay, so let us analyze the situation. See, you know that when a current is flowing through a conductor, definitely it behaves as a magnet. Have you seen that when two magnets are kept near each other, what happens? They either attract each other or repel each other, isn't it? So these are the two things that can happen. Okay, so write down the topic name: force on a current carrying conductor placed in a magnetic field. Magnetic field, isn't it? Okay. So this is our topic name. Okay, see, now the fact that we are telling that whenever you place a current carrying conductor, what happens? When the current carrying conductor behaves as a magnet, now you see, if two like poles of a magnet are brought near each other, they repel. That is, if north pole, or south pole, or two magnets are brought near each other, they show a repulsion, isn't it? Okay. On the other hand, if you bring two opposite polarities of a magnet or two magnets, they attract each other. Either the north pole of one magnet and south pole of the other magnet, you will see attraction. So there is either repulsive force or attractive force acting when two magnets are brought close to each other. Now, this is the very basic, the very basic idea, that a current carrying conductor, when placed in an external magnetic field or when placed near a magnet, can experience a force. See, when you are causing a current to flow through a conductor, what happens? When the current flows to, say, this is a conductor, a long conductor. If current flows through this conductor, what happens? A magnetic field is generated around it, isn't it? A magnetic field is generated. So a magnetic field is generated near, at the vicinity of, in the vicinity of this wire. Okay. Now, if, say, there is another magnet near this wire, and this magnet is quite strong. This magnet has quite strong. Say this is a permanent magnet, but it is quite strong. It has a north pole and south pole of its own, and this also creates a magnetic field. Now, due to the interaction of these two magnetic fields, the magnetic field due to this wire and the magnetic field due to this permanent magnet, due to the interaction of these two magnetic fields, what happened? There is a force acting on the wire. If the magnet is kept held at a fixed position, and if the wire is kept in such a way that it can move a little bit, then obviously we will be seeing that the wire is displaced from its position whenever the current is switched on and the wire is kept in the magnetic field of the permanent magnet. So, how can you determine the direction of the force that is acting on the conductor? For that, a rule is applied which is called the Fleming's left hand rule. So, what is the Fleming's left hand rule? Now, I think the concept is clear, that why a force acts on a current carrying conductor. So, if it is clear, then let us see what is the direction of the force acting on a current carrying conductor. For this, what we do, we make application of Fleming's left hand rule. Okay, so what does this rule says? Now, for this rule to be applied, there is one condition, that the magnetic field line, the current through the conductor, that is the conductor itself, should be placed perpendicular to each other. Then only you can get the direction of the force acting on the conductor. So suppose say, using your left hand, consider three fingers, the thumb, the index finger and the middle finger. These three fingers you have to take into consideration. Now let us see. So this is our index finger, okay, this is our middle finger, okay, and this is our thumb. So the thumb is in the, say if I consider the coordinate axis, this is your y axis, say this is your y axis, okay, this is your x axis and this is your z axis. The thumb is in the direction of the z axis, okay. So z, this is y, and say this is x, okay. So if I consider these three fingers like this, I think the figure is clear. Like this, we have considered the index finger and the y axis, the middle finger on the x axis, and the z axis has the thumb in this direction. So here the index finger represents the direction of the magnetic field. So magnetic field, index finger represents the direction of the magnetic field. The middle finger represents the direction of the current, that is the direction in which the conductor is being placed, and then the thumb gives you the direction of the force that is acting on the conductor. So this is the Fleming's left hand rule. So if you just want to have a statement of the Fleming's left hand rule, how can you say that if we stretch our left hand, three fingers of our left hand, the thumb, index finger and the middle finger mutually perpendicular to each other, that is all they are perpendicular, then if the index finger gives the direction of the magnetic field, the middle finger gives the direction of the current flowing through the conductor, then the thumb will point out in the direction in which the force acts on the conductor. So see, if here the magnetic field is in this direction, the current is flowing in this direction, then what happens? The force will act in this direction. So the blue marker represents the current flowing, the black marker represents the magnetic field, then the red marker represents the direction of force. I think the figure is clear. You can rotate this into any configuration, okay. So it is clear. See, these three axes, these three parameters are mutually perpendicular to each other. So this is Fleming's left hand rule, okay. So it is clear. I think the concept of Fleming's left hand rule is clear to all of you. Okay, fine. So this is the force acting on the current carrying conductor. We just have a qualitative analysis. We do not have the quantitative analysis at the plus 10th level, okay. So we will be moving on to the next topic. Now next topic is, so I think you have noticed, I have noted down the concept. If not, please pause the video, move back a little bit and note down the concept. Okay. Very important concept, very helpful also, okay. Now the next topic that we will be studying is the reverse of what was happening in the previous, what we talked about in the previous lectures. The reverse thing, what the reverse thing says that, now when if a current through a conductor can generate a magnetic field, is it possible in some way that if you move a conductor in a magnetic field, you have just a few minutes back you have seen that a current carrying conductor placed in a magnetic field experiences a force, isn't it? You can determine this direction of the force by the Fleming's left hand rule. Can you imagine of the reverse thing, that when a conductor is placed in a magnetic field and it is moved, that is force is applied by us a current can be produced in the wire? Have you ever imagined this? Yes, it is 100% possible, and we utilize this principle to generate electricity in the power plants. It is this very principle that we utilize to generate electricity in the power plants. So the next topic is electromagnetic induction. Next topic is electromagnetic induction. Okay, electromagnetic induction. So I have already introduced the concept that if I place a current in conductor, current is not flowing through it in a magnetic field, and mechanically I move the conductor. Okay, mechanically I move the conductor, then obviously it is observed that an EMF is generated in the wire, or you can also say a potential difference is being generated in the wire. And if the wire is in a closed path, you know that until and unless a closed path is available, current cannot flow in a conductor. Although potential difference can be generated, potential difference can be introduced, but unless and until the wire is in a closed loop, no current will flow. Okay, so utilizing this fact, we can say it has been observed also that if the current carrying loop is moved through a magnetic field, EMF is generated, and as a result of that, electricity is introduced or electricity starts flowing in the wire. So this is called electromagnetic induction. So what is the induction process? The process by which you can induce or generate electricity or cause electricity to flow through the wire, isn't it? That very process is termed as electromagnetic induction. Okay, so actually electromagnetic induction, so this is the very concept of electromagnetic induction, and this electromagnetic induction was studied in details and the theories were made available by a scientist called Michael Faraday. You must have heard the name of Michael Faraday. He actually experimented on this very subject and brought this fact in front of the world, and this principle is now being utilized to generate electricity in the power plants. So I think electromagnetic induction is clear to all of you. So we will be discussing about this topic of electromagnetic induction in the next class. So today we will be ending our class here. Okay, in the next class we will be talking about electromagnetic induction and the laws of Faraday. Okay, so today we will be ending our lecture here. This was a brief lecture, as because the two topics was left behind in the previous lecture, so we have covered it up. In the next lecture we will be discussing in details about electromagnetic induction. So till then, thank you, goodbye, take care and study well.